This video is on the problem set that we did for section 11.7, Taylor series. So before you start working problems, it will be so much easier if you really see what these coefficients are and what Taylor's theorem says. Then the problems won't be hard at all. So take a few minutes, be able to write this yourself, write out the coefficients yourself, and know them by heart. We proved in 11.7, we proved it on the video, that if you have a power series representing a function, that the coefficients of that power series are as written here on this slide. For example, the coefficient of x minus x naught cubed will be the third derivative at x naught divided by 3 factorial. The coefficient of x minus x naught to the 10th is the 10th derivative evaluated at x naught over 10 factorial. There is no other way that a power series converges to a function f or represents a function f without having these as its coefficients. So memorize the coefficients. The kth derivative at x naught, where x naught is the number that you are centering your series at. The kth derivative divided by k factorial. Now if x naught is 0, as it is in all 5 of the series that you have on the table that will be given to you on the exam, those series are called, well, they're Taylor series too, but they're called Maclaurin series, where x naught is 0. And in that case, look at the k is up too high there. I don't know why. In that case, you have your coefficients. The kth coefficient in the series is the kth derivative at 0 over k factorial. And there you just have x to the k. It's no different than above. It's just replacing x naught with 0. Taylor's theorem tells us about the accuracy of estimating a function with a Taylor polynomial. Notice p sub n of x here is just the front end of a Taylor series, where you chop off the tail after n terms. And if you do, Taylor's theorem tells you that you can estimate the error by just looking at the n plus first derivative. If you can get an upper bound on its absolute value, then you know that the error committed by the nth polynomial, this is just the error, right? The absolute value between the real function at x minus the nth Taylor polynomial at x, that's the error. The error committed by the nth polynomial, using that instead of the whole thing, instead of the function, that the error will be less than or equal to that upper bound on the n plus first derivative divided by n plus 1 factorial times the absolute value of x minus x naught to the n plus 1. Notice that all this is here, the next term, you chopped it off here, in this slide, we chopped it off at n. The next term would be f, the n plus first derivative at x naught, divided by n plus 1 factorial times x minus x naught to the n plus 1. That would be the next term in the series. Notice this is almost exactly the same thing. We're saying that if you have an upper bound on this, just place that here, and you're taking absolute value, that the error will be less than the absolute value of all that if you have this upper bound. in actuality, if you're estimating, let's say you've centered your series at x naught and you're using p sub n to estimate f of x, in actuality there is a number c in here between x and x naught. There is a number c, so that if you put c in, this is the error. The entire rest of the series, the part that you cut off, is the n plus first derivative at some value of c between x and x naught. Well, we're not going to try to find that c. We're using a little weaker version of Taylor's theorem and just saying, hey, if you can get an upper bound on it, we'll be happy to just get an upper bound on the area, on the error, I mean. Okay, so we'll see how this works in this example. Let's say that f of x is the integral from 3 to x of the square root of t e to the minus t dt. The minute you see that, you should think of the fundamental theorem of calculus. And I wouldn't even read what the question has to say. When you see a function defined with the variable as the upper limit of integration, go over and say to yourself, the fundamental theorem tells me that the derivative of f of x is the square root of x e to the minus x. That's the fundamental theorem. And I also know something about f at 3. I also know that f of 3 is equal to 0. These two things come from the fundamental theorem, so let's write them down, and I guarantee you in this problem we'll be wanting to use that. The way that I wrote the problem in the problem set you see here, another way I could ask this question on the final is to just say, find the second degree Taylor polynomial centered at x naught equals 3 and estimate its error in approximating f of 3.5. So to find the second degree Taylor polynomial, that's what I gave you here, and I just said show that f of x is approximately equal to that. So you needed to show that this was the second degree Taylor polynomial. We know that p2 of x is approximately equal to f of x if x is in the interval of convergence. So all we need to do is find the second degree Taylor polynomial. All right, write it down. This is what comes from memorizing the coefficients. P2 of x is equal to f of 3 plus f prime of 3 times x minus 3 plus f double prime of 3 over 2 factorial, or 2, times x minus 3 squared. Partial credit right there. You know what the second degree Taylor polynomial is. So now we need to obviously find f of 3. We need to take the first derivative and plug in 3, and take the second derivative and plug in 3 and divide by 2. So I'm sure that you can do all this. F of 3 we saw up here. F of 3 is equal to 0. So that's just equal to 0, and we won't put it there. So f prime of x, use your product rule. Oh, we know f prime of x. F prime of x is right here. I told you we'd use that. The square root of x e to the minus x, using the fundamental theorem. So we can easily plug in 3. F prime of 3 is equal to the square root of 3 times e to the minus 3. And look, that's what we have here. So we're done with the first part. F double prime of x, we're going to have to use the product rule. So you differentiate f prime using your product rule, and you get, let's see, I want you to just do this. There's no need for me to write all this out. Well, using the product rule, I got 1/2 x to the minus 1/2 times e to the minus x minus x to the plus 1/2 e to the minus x. So you need to take f double prime at 3 and just do this on scratch paper. F double prime of 3 does turn out to be minus 5/12 times the square root of 3 times e to the minus 3. That'll take a little bit of simplification, but you go ahead and plug in 3 and that's what you'll get. So really, oh gosh, sorry. So P2 of x is exactly this. This right here, this is what we just figured out. And in answer to this question, you would say f of x is approximately equal to this because this is the second degree Taylor polynomial. In the next part, we will estimate the error. This says use Taylor's theorem to bound the error made when f of 3.5 is estimated using the polynomial that we found in part A, P2 of x. Okay, so I gave you, and I would on the graph, give you a graph of the third derivative. So we know that the third derivative is, well, if we can get a bound on the third derivative at 3 over 3 factorial times x minus, well, 3.5, here I'll write it, 3.5 minus 3 cubed, then we will have an estimate, an upper bound on the error. But first we need the, here I'll go, we need absolute value signs there. First we need to get an upper bound on the third derivative. So I gave you a graph of the third derivative. Now it has to be an upper bound on an interval containing 3 and 3.5. So look, from x equals 2 on, you can see that the third derivative is decreasing. So let's get really close to 3. I think I'll just pick 2.9. Now if you pick 2, that's okay. But I know that the third derivative evaluated at 2.9 will be an upper bound. Will be an upper bound. On the interval, on an interval containing 3 and 3.5. So I need to calculate the third derivative, and you go ahead and do that and find that the third derivative, I mean, you've got to use your product rule and just grind it out, and you will get that well, here, let me tell you what the third derivative is. It's minus 1 minus 4x plus 4x squared over e to the x. And this tells me that the third derivative at 2.9, using my calculator, is, well, it's to 3 decimal places, it is 0.058. And that's what we pick for our upper bound that we call K3. So now let's write what Taylor's theorem gives us. The absolute value of f of 3.5 minus the estimate P2 of 3.5, what you get by plugging it into the polynomial, that's the error committed, and that is going to be less than our K3 0.058 over 3 factorial, which is 6, times the difference, the positive difference, is 0.5, 3.5 minus 3 cubed. And put that into your calculator and you get 0.0012. So the second degree Taylor polynomial gives us an excellent estimate of the function at 3.5. Notice we did choose to center it at 3, a number close to 3.5. If we centered the polynomial at 1, we would have to go out much further in our derivatives, finding coefficients. We would have to go out further and find a longer Taylor polynomial that would do a good job at estimating 3.5. Number 2 is a question very similar to the one that we just did. It says find the first 3 non-zero terms in the Maclaurin series. So in other words, we know that we're centering here at x naught equals 0, and that our first few terms are f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial times x squared plus, and I'll go out to the third here, we may not need it, x cubed. This question just wants the first 3 non-zero terms, so that's all we'll need to answer the first part A of the question. Well, we see, f of 0 we just get by plugging in 0. Square root of 1 is 1. So f of 0 is 1. We need to take the derivatives. So I'm going to take them. You should put it on pause right now and make sure that you also can get these derivatives easily. I would write 1 plus x to the 1/2 for differentiation. And you get f prime of x is equal to 1/2 times 1 plus x to the minus 1/2. The derivative of the inside is 1, so we don't need the chain rule. F double prime of x is equal to minus 1/4 times 1 plus x to the minus 3/2. And we're going to need the third derivative on the next part of the problem, but I'll wait and take it then. This is all we need for now. We see f of 0 is 1. F double prime of 0 is equal to, well, 1 to the minus 1 to any power is 1, so it's just 1/2. And that was f prime, excuse me, and f double prime of 0 is equal to minus 1/4. I'm more apt to put something like this on the final than I would be that first question where there's a lot of simplification and arithmetic that you're doing. This one's nice. Okay, so our answer is we just needed the first 3 terms, and once we have those derivatives, we have the coefficients. 1 plus f prime of 0, 1/2 times x, and now it'll be minus f double prime of 0. Well, let's see, f double prime of 0 over 2 is equal to minus 1/4 over 2, which is minus 1/8, times x squared. So this is P2 of x. It is the first 3 non-zero terms of the Maclaurin series for the function square root of 1 plus x. So for part B, we want to find out if we used that Taylor polynomial that we centered at 0 to estimate f of 1, what would the error be? Could we get an upper bound on it? So we need the third derivative, and the third derivative is, just go back to part A and take the derivative of the second derivative, and you get 3/8 times 1 plus x to the minus 5/2. That is given to us here in the graph of the third derivative. Now I see that, it's decreasing from 0 to 1, and I need to find an interval that contains 0 and contains 1, and I want to have an upper bound on the derivative there. Now I went a little bit to the left of 0 and I chose minus 0.1. So In other words, I'm going to get an upper bound right there. So f triple prime of minus 0.1 using your calculator is 0.488. So that I'm using, it's this number right here, as an upper bound on the derivative. So this is my K3, an upper bound on the third derivative. This gives us then, just like in the example before, an estimate on the error that the second degree polynomial would give us. So let's see, the function was the square root of 1 plus x. So, well, let me write. It's f of 1 minus p2 of 1. That would be the error. And f of 1, that's the square root of 1 plus 1, minus p2 of 1 is 1.5 minus an eighth. And calculating that, this is equal to, correct to 3 decimal places, 0.039. So our estimate is within 4/100ths of being correct. Oh, that is the actual, oh, excuse me, just a sec. What we calculated there was the actual error. So now we want to see how good the polynomial did. I'm sorry. So now we have our value of K3 is 0.488, and now we'll calculate using Taylor's theorem. We would find out that the absolute value of the difference between the functional value and the polynomial would be less than a 0.488 over 3 factorial times the difference between 1 and 0, so that's 1 cubed, 1, and that is equal to 0.08. So using minus 0.1 as my f double prime of minus 0.1 as my upper bound, using 0.488 as K3, in other words, I got an upper bound on the error. And you see, indeed, it is bigger than the actual error. Now, in applications, if you knew what the actual error was, if you had a way of calculating that easily, why in the world would you do an approximation? So keep in mind, these are just problems to illustrate how you use Taylor's theorem. In practice, you really wouldn't know what the error is, because the whole point of approximating would be the fact that you couldn't calculate f at x naught. Instead, you were calculating a Taylor polynomial at x naught, and then you would need an estimate of what the error would be. If you tried to do it and the function didn't converge there, well, then your error would be huge, and you wouldn't use the polynomial to approximate. Now, problem 3 is using the fact that we know a series for e to the 2x. We know the series for e to the x, and so to get e to the 2x, we plug 2x in for x, just like we do in the function. So e to the 2x would be, using summation notation, the sum from n equals 0 to infinity of not x to the n, but 2x to the n over n factorial, which is the sum from n equals 0 to infinity of 2 to the n over n factorial x to the n. So the coefficient of x to the 100, we know exactly what it is. It's this. The coefficient of x to the 100 is 2 to the 100 over 100 factorial. Very easily solved. And you see here, it's nice to use the sigma notation because you have the generalized version of the coefficients. Notice I put in a couple more questions here to give you a little more practice, because these are easy questions to answer, and they do test whether or not you understand the coefficients of Maclaurin or Taylor series. So let's see, what is the coefficient of x to the 100 in the Maclaurin series for sine x? Well, let's write the series. It's on your list. It's the sum from n equals 0 to infinity minus 1 to the n over 2n plus 1 factorial times x to the 2n plus 1. If you wanted to write out a few terms and you were confused, well, how would I get the 100th, x to the 100th? You could write out a few of the terms. When n was equal to 0, you have x and then minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus, well, what is the coefficient of x squared here? It's 0. What's the coefficient of x to the 4th? 0. Because the even powers of x all have coefficients of 0 in the series for sine x. So we say the answer here is the coefficient of x to the 100 is 0. Now for cosine x, I would write the series cosine x is equal to the sum from n equals 0 to infinity minus 1 to the n over 2n in parentheses factorial x to the 2n. Well, this time all of the odd powers of x have coefficients of 0, and we see that when n is equal to 50, we have x to the 100th power. So when n is equal to 50, the coefficient is minus 1 to the 50th over 2 times 50, 100 factorial, which is which is 1 over 100 factorial. So there we get a non-zero coefficient of x to the 100. This problem I asked you to do in two different ways. We know what 1 over 1 minus x looks like. We've looked at it many times in class. And this time, instead of centering our Taylor polynomial at 0, we're going to center it at 2. So one way to find these coefficients is to start taking derivatives and see if we could find a pattern. But there's also a simple way in this case, because we can look at 1 over 1 minus x as minus 1 over 1 plus x minus 2. And we know from our chart 1 over 1 plus x is the series sum from n equals 0 to infinity minus 1 to the n, x to the n. We got that by plugging minus x into the sum of the geometric series, sigma x to the n. So since we know that, we can just take x and replace it with, if we replace that with x minus 2 and put a minus out in front of it, we've got exactly what we need. Put a minus in front of the series and replace x with x minus 2. So that gives us the sum minus the sum from n equals 0 to infinity minus 1 to the n, x minus 2 to the n. So we're almost done. This is minus a big long infinite sum. I'm going to bring that factor of minus 1 in and multiply it to every single term. So I get the sum from n equals 0 to infinity. Now notice, all I'm doing here is taking minus 1 and multiplying it to minus 1 to the n. And that gives me minus 1 to the n plus 1. So I will do that here. Minus 1 to the n plus 1 times x minus 2 to the n. So our coefficients are, we wanted to find, it said find the coefficients. So I had to multiply that minus 1 in, and I see that the coefficients of x minus 2 to the n is simply a sub n is equal to minus 1 to the n plus 1, or a sub k is equal to minus 1 to the k plus 1. That's our coefficient. And, by the way, we know that that is equal to, let's just do a little sidelight because this is the next way we're going to solve this problem. We know that that is the coefficient of the Taylor series centered at 2. So that is, we know, f, the nth derivative at 2 divided by n factorial, where f of x is 1 over 1 minus x. That's what we've got to prove if we actually have to take derivatives and try to find a formula for the nth derivative at 2. A much more complicated process than just being able to recognize this as function composition with 1 over 1, with the series for 1 over 1 plus x. So now we'll do it using the definition of the Taylor series, the Taylor coefficients. Watch carefully because there's a good chance I will ask you to do this. Maybe not to discover the entire series to get a pattern because it's a matter of time on the final, but certainly you will have to solve for some Taylor coefficients. So let's see, our function is f of x equals 1 over 1 minus x, which is 1 minus x to the minus 1 for taking derivatives. So we'll need a few derivatives. F prime of x is equal to 1 minus x to the minus 2. And you see how you get these. You get minus 1 times 1 minus x to the minus 2 times minus 1 using the chain rule. This coefficient turns out to be positive. And you check to make sure that you can get these derivatives using the chain rule. The next one is 2 times 1 minus x to the minus 3. The third derivative is equal to 3 factorial, and notice 2 is 2 factorial, and this is 1 factorial, so we're kind of seeing a pattern here. 3 factorial times 1 minus x to the minus 4, and let's do another. The fourth derivative at x will be equal to 4 factorial times 1 minus x to the minus 5. So you're beginning to see a pattern there. Now let's plug in 2 into these. I'll use a different color. So now we want to plug in 2. Well, f of 2 is minus 1. F prime of 2, plugging it into the derivative that we got, we have 1 factorial. And f double prime of 2, we will get minus 2 factorial. F triple prime of 2, we're going to get 3 factorial. And the fourth derivative at 2, we get minus 4 factorial. And that was when n was equal to, we need to keep track of our value of n equals 0, n equals 1, n equals 2, n equals 3, n equals 4. So from this, we can get a pattern for the kth derivative at 2 and divide it by k factorial. Alright, so let's see, when n is equal to 0, well, 0 factorial is okay, that's equal to 1. So you look at these and you will see that the nth derivative at 2 is equal to minus 1 to a power, and it's n plus 1 because we want it to be positive when n is odd and negative when n is even. Negative when n is even. So instead of minus 1 to the n, we write minus 1 to the n plus 1, and then it's just times n factorial. And now we want to divide by n factorial. So divide by n factorial to get our Taylor coefficient. So a sub n is equal to minus 1 to the n plus 1. And that's what we got doing it the more simple way. You don't always have a simple way to do it though. And in fact, usually you're not going to be able to find a nice pattern like this and solve generally for the coefficients. But you can always grind out the first few derivatives and find the second, third, fourth degree Taylor polynomial, and you can estimate the error that you would have in using it at a particular value of x. Problem number 5, the last problem in this set, is similar to what we've done before. Find the Maclaurin series for f of x. Well, there's no need for us to try to find a general form like we did on the last problem for the kth coefficient of the Maclaurin series, because we can use series that we already know. This function, f of x, is equal to x times 1 over 1 minus x cubed. So all I have to do is take x cubed and plug it into the series for 1 over 1 minus x. So that's what I'll do. And I'll have to multiply by x, and then I'll have the sum from n equals 0 to infinity of x cubed to the n, x to the n. So this is x times the sum from n equals 0 to infinity of x to the 3n, multiplying your exponents. And now I multiply x to each and every term in the infinite polynomial, and I get n equals 0 to infinity of x to the add 1 to every exponent, 3n plus 1. Now you do not have to use summation notation. You could go through this by just using the other form that it's written in on your little table of series. What is the interval of convergence? Well, we just used the geometric series for 1 over 1 minus x, sigma x to the n. So here what we plugged in for x was x cubed, so we know that the absolute value of whatever we plugged in has to be less than 1, because the interval of convergence for sigma x to the n is absolute x less than 1. Well, minus 1 less than x cubed less than 1 is exactly minus 1 less than x less than 1. So the interval didn't change. But you have to check that. If I had plugged in, for example, x over 3, then I would have changed the interval to minus 3. So you do have to check. So here, for those of you that are not using sigma notation, your answer to part B, or to part A, would have been, let's see, it would have been x, your function f of x would be x plus x to the 4th plus x to the excuse me, no, that's not right. Yeah, that was right. So I wrote it out in the more simple form, polynomial type form, and also the way that I did it in part A using summation notation. And this part just says find a power series for its second derivative. Well, you just take the derivatives. F prime of x would be 1 plus 4x cubed plus 7x to the 6th plus 10x to the 9th plus, and so on. Or if you did it here, the derivative, let's see, when n is 0, you do have x. So n will continue to go from 0 to infinity. You're not losing that first term. And you have a 3n plus 1 times x to the 3n, subtracting 1 from the exponent. And now our answer will be f double prime of x is, this time the first term drops out. We have 12x squared plus 42x to the 5th plus 90x to the 8th, and so on. Or, writing it in this notation, this time the first term drops off, because when n is 0 you have a constant. So I'll put the sum from n equals 1 to infinity of 3n times 3n plus 1 times x to the 3n minus 1. Either way you want to write it is fine. The interval of convergence does not change when you integrate and differentiate series. So in part B we said the interval was -1, 1, and it would remain so if you integrate or differentiate series. So the last question, use part A to find the Maclaurin series for the integral from 0 to x of f of t dt. What do you think of when you see that? Always the same thing. You better have thought fundamental theorem of calculus. I know that if this function is called capital F of x, the integral from 0 to x of little f of t dt, which we were given in part A, I know that f prime of x is little f of x. And so I am going to that tells me that what I will do to get a series for this, I will integrate. I will just integrate the series for f of x and make sure that it is equal to 0 when x is equal to 0. Because this isn't just the entire family of antiderivatives, is it? This function is not the entire family of antiderivatives. It's not just the indefinite integral of f of x dx. It's a particular one. It's the one that equals 0 when x equals 0. So I will say capital F of x will be equal to the integral of the sum from n equals 0 to infinity of x to the 3n plus 1 from part A. And that, I know, is equal to, I can integrate term by term. N equals 0 to infinity, and now integrating here, I will get x to the 3n plus 2, and I multiply by its reciprocal, 1 over 3n plus 2. So there we have the series, and let's make sure that it is equal to 0 when x equals 0. So you might write out the first. We just want to make sure the first term's not a constant. So when n is equal to 0, you get 1/2 x squared plus, and so on. All of these have x's. So this implies that f of 0 equals 0, and so this is our answer.